Welcome everyone. This is a discussion on collaborative processor performance control or CPPC as applied to ARM platform. CPPC is a mechanism for OS to collaborate with platform firmware to manage the performance of a processor. This discussion focuses on ARM v8.4 system onwards, which has the architected AMU counters. A quick introduction about myself. I am Pranav Madhu, software engineer in the open source group at ARM. My major focus has been on enabling power management functionality for newer platforms. In the next 20 minutes, I'll be talking about CPPC as applied to ARM platforms for controlling the processor performance. This discussion also gives an overview of the activity monitoring unit extension or the AMU extension and the SCMI Fastchannel, which are the two components required in achieving the CPPC functionality. And at the last part, the discussion is about how to monitor and control the CPU performance using Linux SysOS entries. So CPPC is a mechanism for the OS to manage the performance of a processor core on a contiguous and abstract performance scale. CPPC is required for power management as well as for thermal management. For example, consider a system running at its maximum throttle and the CPU load is also very less. In that case, there is no point in running the CPU at the highest performance as the load is very less. So in that situation, it is recommended to reduce the CPU frequency or the CPU performance to a lower value for saving power. And another scenario is where the system runs above the allowed thermal range. So in that condition also, using the passive thermal management, it is recommended to bring the CPU to a lower frequency for reducing the system temperature. So how CPPC works? CPPC for CPPC, the OS requests the platform firmware the required performance over some platform communication mechanism. So the OS will request the required performance to the platform firmware, and the platform firmware will update the CPU frequency and voltage if the performance level requested by the OS is supported in the platform. The ACPI CPPC specification has put four thresholds in the CPU performance scale. Among this, the highest performance is the highest level of performance a processor can achieve, or the highest frequency and voltage is referred to as the highest performance. The nominal performance is the highest sustained performance a processor can deliver, and it is not recommended to keep any processor above this nominal performance for longer, as it may result in thermal instabilities or trade-off in efficiency. The lowest nonlinear performance is the lowest performance level at which nonlinear power savings are achieved. Keeping a processor below this level results in efficiency penalty. And the last threshold is the lowest performance, and which is the absolute lowest performance level a processor can achieve. It is not recommended to put the processor in lowest performance, but in some scenarios for this making the system or bringing the system back to normal or allowed thermal range, uh, it may be required to bring the CPU to this lowest performance. And also between these thresholds, for example, between the nominal performance and the lowest nonlinear performance, there can be no, one, or more than performance level. And yeah, and the CPPC framework implemented in ARM platforms has two parts. One is the performance monitoring part, and the second is the performance controlling part. On the performance monitoring part, it uses the activity monitor or AMU registers to obtain the CPU performance, or using the AMU register values, the OS will calculate the operating frequency. On the next half, performance controlling. On performance controlling, the OS will request the desired performance to the platform firmware over fast channel or the SCMI fast channel, and on receiving the performance change request, the platform firmware will check whether the requested performance level is supported. If the level is supported, then the platform firmware uses the DVFS framework to update the frequency and voltage of the respective core. As discussed in the previous slides, the activity monitor unit or the AMU registers are used in monitoring the processor performance. So yeah, the AMU extension is an optional extension which is introduced in the ARM 8.4 architecture. The AMU consists of a group of 64-bit event counters, which are classified into two groups: the architected event counter or the group 0 counters, and the auxiliary event counter or the group 1 counters. So each of these architected event counter or the auxiliary event counter, each of these are 64-bit event counters, and there is one control register for controlling each of these registers independently. The events counted by the architected event counters are fixed and architecturally defined, and the event counted by the auxiliary event counter may be fixed or programmable. It's purely implementation defined. For AMV1, AMV1 has 4 architected event counters and 16 auxiliary event counters. For the performance monitoring, the architected event counters used are the performance frequency counter and the constant frequency counter. On monitoring the performance, so in this slide, the processor frequency counter is also referred as the delivered performance counter, and the constant frequency counter is referred as a reference performance counter. So yeah, in calculating the uh, delivered performance or deliver or the current of frequency of the CPU, so the reference performance counter as well as the constant frequency counter are the reference frequency counter and the processor frequency counter are red, and which are kept as set 1 reading, and after the set 1, wait for some time, say for some 2 microseconds. So after the delay, again read the processor frequency and the constant frequency counters, and now there are two sets of reading. Based on these two sets, calculate the delta between these two sets, and using this, the delivered performance can be calculated as reference performance into delta delivered divided by delta reference. So in this calculation, the reference performance is known, and the delta delivered and delta reference will be obtained from the AMU counter values. So once the delivered performance is available, which can be converted into frequency and can be sent to the OS. One thing to be noted is that the AMU counters will not increment or will not increment the count when the respective core is in WFI or WFE. The AMU registers are implemented as system registers which are not memory mapped. So the recommended method in accessing such platform specific register is the fixed hardware or fixed feature hardware interface as recommended by the ACPI specification. So yeah, in this case, the delivered performance counter is having the fixed hardware address of 0, and the reference performance counter is having the fixed hardware address of 1, and the kernel has a support for handling this or the mainline kernel has a support for handling the delivered performance address as well as the reference performance address in the fixed hardware address space. So for the CPPC functionality, so the second half or the controlling of the processor performance, the SCMI Fastchannel is used as the communication medium between the OS and the platform firmware. So Fastchannel is a memory mapped region shared between the application processor and the platform firmware. So Yeah, and also for controlling the performance of each core independently, it is recommended to have one fast channel per core. And a single fast channel supports four protocols: the performance limit set, performance limit get, performance level set, and performance level get. The performance level set protocol is the protocol used by OS for requesting the desired performance to the platform firmware. On controlling the processor performance, the platform firmware will configure the timer to generate an event or generate an alarm periodically for the SCMI perf driver on boot. For say for some 4 millisecond, every 4 millisecond, the timer timer subsystem will generate an event for the SCMI perf driver. So on boot complete or at the runtime, the Linux based OS or whatever OS is running, the OS will request the performance level to the platform firmware or SCMI fast channel. So yeah, or the OS will write to that shared memory, and whenever the timer event is generated, the SCMI perf module will read the fast channel, and if there is any uh, value update or if the value got changed, then it will inform the DVFS module, and the DVFS module will configure the operating frequency as well as the voltage of the AP core if the performance requested by the OS is supported in the platform. The previous slides discussed about CPPC overview, the components involved in monitoring and controlling the performance for ARM-based platforms. Moving ahead to the software implementation, the CPC control method under the CPU object should specify the below fields, that is from the highest performance till the nominal frequency. These many fields should be exposed as or should be specified as integer values, and the delivered performance counter and the reference performance counter should be implemented as this F fixed hardware or feature fixed hardware, and the performance level set register or the fast channel register or the fast channel protocol should be implemented as a system memory. So these are the required fields for the ACPI CPC package. So other than the CPC package, it is also required to declare the underscore PSD or P state dependency control method also under each of the CPU object. Uh, also on making the performance scale, platform must use the same performance scale for all processors in the system. For example, consider a big little system. The big CPU will run at a higher frequency and the little ones are lower. In such a system, any two processors running at the same performance level should finish the same workload in approximately same time. So yeah, this is why it is recommended to choose same performance scale for all the processors in the system. And the performance granularity should also be chosen such that the reference performance is an integer. Consider the example below. So here in the system, the reference performance is 100 megahertz and the granularity chosen is 20 megahertz. So it will give the reference performance as 5. So it is not it is not it is not recommended to choose the granularity as 30 megahertz because in a 100 megahertz system with a granularity of 30 megahertz, the reference performance will be 3.33, which is a floating point, which is not recommended. So care should be taken in fixing the reference performance or choosing the performance scale granularity. And also the highest performance and the nominal performance should be exposed as integer values, and the uh, desired performance register as well as the desired performance register is exposed as the system memory, and the reference performance counter and the delivered performance counter are configured as the fixed hardware. Now on the DVFS configuration, the DVFS configuration at the platform firmware side should also map each of the performance level supported with the respective frequency and the voltage level. So yeah, this is the performance level or the performance value uh, in the scale which is chosen, and the corresponding frequency mapping and the voltage mapping for the respective performance level should also be mapped in the DVFS framework. This slide is specific for Neoverse reference design. So this the software components involved for Neoverse reference design are the boot time components are in the platform firmware side. The platform firmware need to initialize the PSU or the power source unit, then the DVFS dynamic voltage frequency scaling system, and the SCMI drivers on boot. And also at boot, the platform firmware need to configure the timer to generate an alarm for polling the fast channel at regular intervals, say some 4 milliseconds or whatever is the proper value. From trusted firmware, the trusted firmware should enable the AMU registers or the AMU counters, and also the trusted firmware need to make the AMU registers accessible to the non-secure OS. And the runtime part, on the runtime, the platform firmware, the SCMI driver should poll the fast channel periodically based on the alarm generated by the timer module, and based on that it need to the SCMI perf module need to generate events for the DVFS module. And on the UEFI part, majority of the changes are there in the ACPI, especially in the CPC control method. So in the CPC control method should provide the fast channel address as well as the AMU register address as F fixed hardware or feature fixed hardware for the OS. And also in the UEFI or in the ACPI table, the PSD or the psted dependency control method should also be declared under each of the core. On Linux part, it is majorly on the governor and the CPPC driver, which evaluates the undercore the CPC control method. And yeah, the kernel need to monitor and scale the performance accordingly based on the entries provided in the ACPI table. So for a Linux system, Linux by default boot with the schedule governor, and on boot time there will be more load at the CPU, and the kernel requests the platform to switch to nominal performance, as nominal performance is the sustained performance or the great or the highest sustained performance a CPU can run at. So the schedule governor will request for nominal performance, and once boot complete, the CPU load will be less, and the schedule governor will request the platform to switch the CPU to lowest nonlinear performance. So yeah, that's about the schedule governor. And for evaluating the CPU frequency and the performance and related stuffs, the sysfs entry for CPC is available at this path in the Linux sysfs. So this so here x can be 0 to n. So for example, in a system with 8 CPU, the x can vary from 0 to 7. Yeah, and here I look into the policy 0. So let's take an example CPU 0. So on reading the scaling available governors, will give the available governors or the governors supported by the driver. Oh, sorry, the driver supported by the kernel. In this case, the drivers supported are on demand, user space, performance, and scheduled governors. And on reading the scaling governor, will display the governor which is currently in use. In this case, it is a scheduled governor. And on reading the CPU info curve frequency or CPU info current frequency, this particular CFS entry, the driver or the kernel driver will read the AMU registers and calculate the current operating frequency of the CPU, and it will be displayed. This is about the scheduled governor. So now on the configuring part, so if it is required to configure the CPU frequency, so go to write user space governor into the scaling governor, so that the scaling governor will be updated to the user space governor instead of scheduled. And now read the CPU current frequency. Currently it is somewhere around 1.3 gigahertz. Now write the desired performance to scaling set speed, and again read back the CPU current frequency, which will give the whatever frequency is set to the scaling set speed. Yeah. On further reading on the topics discussed in this discussion, it is recommended to go through these documents. Yeah. Thank you.